Page 3 of Math Induction, 9b. We use the notation P subscript n to represent a proposition which is defined for every integer n, where n is greater than or equal to a number a, and a is an integer. So math induction is a formal proof that a proposition is true. Suppose P subscript n is a proposition which is defined for every integer n is greater than or equal to a, where a is an integer. If the first proposition, where n equals 1, P subscript 1 is true, and if P of k plus 1 is true whenever P of k is true, then P subscript n is true for all n greater than or equal to a. So some people talk about how math induction is like a domino effect, where if you show that this is true, where P of k is true, leads to P of k plus 1 is true, then you can show, by showing that P of 1 is true, then you can show that P of 2 is also true, because look, if you show that P of k true leads to P of k plus 1 true, then P of 1 true leads to P of 2 true. And if P of 2 is true, then that leads to P of 3 is true. And so on until you get to infinity, right? So that's the principle of math induction. So let's prove that 3 to the power of n plus 1 is divisible by 2 for all integers greater than or equal to 0 by using two different methods. The first method is we're just going to use binomial expansion, and we're going to express 3 exponent n as 1 plus 2 exponent n, which is the same thing as 3 exponent n. But the thing is, 1 plus 2 exponent n looks like a binomial to a power, and so we could use binomial expansion to expand it, right? And after that, we're going to show how maybe it's easier to do by mathematical induction. Okay, so first what we're going to do is we're going to take a look at this, and we're going to expand it using the binomial expansion. So we don't know why we're doing that yet, but they told us to do the binomial expansion, so we're going to do it, okay? So if you have 1 plus 2 to the n, remember binomial expansion, if you have a plus b to the n, you can expand it using Pascal's triangle, the nth row of Pascal's triangle. So here we have a equals 1, b equals 2. So let's take a look at this. So that would be a to the nth, so it would be 1 to the nth, plus, and then we start using Pascal triangle coefficients, and chooses 1, 1 n to the minus 1, 2 to the 1, plus, and chooses 2, 1 to the n minus 2, 2 to the 2 squared, plus dot, 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 and then we go all the way to the other end of the polynomial. And then we have n chooses n minus 1, 1 to the first, 2 to the n minus 1, and then finally we have the last coefficient, which would be 2 to the n. Let's make this a little bit more compact. Okay. So once we have this, remember also that it's not just 3 to the n plus, or 3 to the n, it's 3 to the n plus 1. And here, let's see, remember that we're going to make this 3 to the n plus 1. So we want to do the binomial expansion of 1 plus 2 quantity to the n plus 1. So we're going to add 1 to this. And you see how there's a 1 here and a 1 here? 1 to the n is just 1, right? And 1 to the any power is 1. So we can add these together and make it 2. And then after that, we just have everything else that's here. So let's just, maybe we'll just copy it. Actually, we didn't need that last one, did we? Oops. Didn't mean to do that. Okay. Oops. Okay. Okay, and then we can erase this because we don't need that, right? All right. So now what we're going to do is we want to show it's divisible by 2. And you'll see as we do these problems that one of the ways of showing that something is divisible by 2 or some other integer is if we finally get at the end, get something like 2 times, some other number, which is an integer, is the number itself, then you can say, oh, well, then it's divisible by 2, because if you factor it, it's got 2 and some other integer. So that means it's divisible by 2, right? So the way we can do that is we can factor out 2 here, and then we'll have 2 times some expression, and then we're going to show that that's an integer, okay? So we got 2 plus n to the 1. Oh, n to the 1, or n chooses 1. N chooses 1 is 1. So then 1 to the n minus 1 is 1. So we just have 1 plus 2. Oh, but we factored out a 2, so it's not even 2. It's 1 plus 1. Then we have plus n chooses 2. We don't know what that is because we don't know what n is. We know n chooses 1 is. Oh, I'm sorry. N chooses 1 is. N chooses 1 is, sorry, n. It's not 1. This is n. And so n chooses 2. 1 to the n minus 2 is 1. 2 squared, we're going to factor out 2, so we're left with 2. Until we get to the other side, and then we have n to the n minus 1, and we know that n to the n minus 1, or n chooses n minus 1 is n. 1 to the first is 1, and 2 to the n minus 1 is going to be 2 to the n minus 2, because we're going to factor out a 2. And then finally the last one, instead of 2 to the n, it's going to be 2 to the n minus 1. Okay? And then if we take a look at this, we know that n is an integer, right? Because they said integer is n. So n is an integer, so that's an integer. N chooses 2, integer chooses 2, that's also an integer. 2 is an integer. Integer, 2 to the n minus 2. You might think that that might have an n value that's less than -2, but it won't, because the n value in this case is big enough so that all the powers of 2 are going to be integers, positive integers also. So all these elements here are integers, and when you add them all up, it's just another big integer. So if you have 2 times an integer, let's say 2 times a, and a being an integer, then we know that this expression here is divisible by 2. And if it's divisible by 2, that means that 3 to the n plus 1 is divisible by 2. Okay, so we have arrived at the end of our proof. Okay, now we're going to use math induction to prove the same proposition. Okay, so this time, so the first thing we're going to do is we're going to show the base case is true. So if n is equal to, and it looks like n starts with 0, so if we say if n is equal to 0, then let's see, 3, so if n equals 0, it'd be 3 to the 0 plus 1 is divisible by 2. So let's see if that's true. 3 to the 0 is 1, so 1 plus 1 is divisible by 2. That's true, right? Okay. So P, therefore P of 0 is true. So if P of k is true, now this is the step case where we're going to assume first that step k is true, and then we're going to see if that implies that k plus 1 is true. So if p of k is true, then we know that we're going to take this expression, we're going to substitute k instead of n, so we say then we know that 3 of k plus 1 is divisible by 2. So it's equal to 2a, where a is an integer. Okay, so we have an expression which illustrates this. Now what we're going to do is we're going to check the case of k plus 1. So we're going to take this expression, and instead of n, we're going to put 3 of k plus 1. So 3 of k plus 1 is equal to, and now what we try to do is we try to make it look like this case here, okay, so that we can substitute in 2a somehow. So we know how to do that. If we know that the exponent is 3 of k plus 1, 3 of k plus 1 is equal to 3 of k times 3 of 1. So we got that. And then let's do this. Let's factor out a 3. And then we have 3 of 3k, 3 to the k, and let's put plus 1 just like we have here, and then we'll do minus 1 plus 1/3. Okay, now we have 3 of k plus 1 right there, right? Now we can substitute in 2a. So I have 3 times 2a minus 2/3. And we can just multiply the 3 out now, so it's equal to 6a minus 2. So let's see, and what we're trying to do is to prove that 3 of k plus 1, 3 to the k plus 1 plus 1 is divisible by 2. And the number that we have equated it to, which is 6 times an integer minus 2, is also divisible by 2, because we could factor out a 2 here, and then we'd end up with 2 multiplied by the quantity 3a minus 1, and this is an integer, right? Because a is an integer, so 3a is an integer, and if you subtract 1, it's still an integer. So since it's 2 times an integer, it is divisible by 2. So thus, 3 of k plus 1 is divisible by 2. If 3 of k plus 1 is divisible by 2. So whenever this is true, this is also true. So that is the second part of the step case for math induction. And so now, like the last statement, it just looks like this. Since p of 0 is true, and p of k plus 1 is true whenever p of k is true, then p of n is true for, and then we just say which values of n it's true for. So it's true for integers. N is an element of the integer set, and n is greater than or equal to 0. Okay? All right, now let's go to 3a. So 3a, we're going to use math induction to prove that n cubed plus 2n is divisible by 3 for all positive integers n. So all positive integers n, that means that n is an integer and n is greater than or equal to 1, right? So for the first statement, the base case, we're going to say that n equals 1. And then we're going to try to state what that means. When n equals 1, let's see if that's true. So n cubed plus 2n, if we substitute n equals 1 into it, would be 1 cubed plus 2 times 1, which is equal to 1 plus 2, which is 3. And so that is divisible by 3. So, therefore, P subscript 1 is true. Okay? So that was easy, right? Usually the base case is easy. Now, if P of K is true, then what can we say? So we'll say we're going to substitute the K's in for the N's here. And so we're going to say then K cubed plus 2K is divisible by 3. And the way we say it's divisible by 3 is we say it's equal to 3 times A, where A is from the set of integers. Now we're going to go to the step case. So the step case, well, we were in the step case already. We're in the step case right there, right? But now we're going to do the K plus 1 case. So the way we do the K plus 1 case is we put K plus 1 into this equation. So we're going to have K plus 1 cubed plus 2 times K plus 1. And now what we want to do is we want to manipulate this with algebra until we get a statement where it's like, look, it's equal to 3a or something obviously divisible by 3. Now, in order to do that, one of the things we're going to try to do is we're going to try to make this look like this. If we can do that and replace it with 3a, then we're going to introduce 3a in there, and then we're going to try to make it so that this expression is 3a. Okay? So let's see if we can simplify this. We're probably going to have to expand it. So let's do a binomial expansion on k plus 1 cubed. So we get k cubed plus 3k squared plus 3k plus 1. And then we'll multiply that out. So we'll get plus 2k plus 2. And then let's try to substitute in this. So do you see how this is k cubed plus 2k? And we do have k cubed plus 2k here, don't we? So we could replace k cubed plus 2k with 3a, right? So let's do that. So now we have 3a, which we replaced k cubed plus 2k with 3a. And then we got everything left over. So we got plus 3k squared. We got 3k. And we also have plus 3 because plus 1 plus 2 is plus 3. Oh, we're getting very close now. Now, do you see how we can factor 3 out of everything? So we have 3 times a plus k squared plus k plus 1. So now we know that that is the factor 3, and this, the other factor, is an integer. And we know it's an integer because a was defined to be an integer, k is also defined to be an integer, and it's squared, so it's another integer, plus k, which is an integer, and plus 1, which is also an integer. If you add up a bunch of integers, you get another integer. So we have 3 times an integer, so we know that it's divisible by 3. So we can say a statement that k plus 1 cubed plus 2 times k plus 1 equals 3a. We could say b because we already used a. 3b, where b is an integer. So it's divisible by 3, right? You could also say it's divisible by 3. Let's say that instead. Divisible by 3 if, and then we say the P of K place, P of K case. So k cubed plus 2k is divisible by 3. And then we just end it with, since P of, in this case, P of 1 instead of P of 0 is true, and P of k plus 1 is true whenever P of k is true, then P of n is true for, and then we just say what n it's true for. It's true for n is an integer, and n is greater than or equal to 1. Another way to say that would be n is a positive integer. Okay? So that is 3a. And that is the end of this page.